Welcome to the radar engineering course. So now we talk about that what is the false alarm time. So for each and every pulses we are receiving, it has some particular duration. That's why we say that pulses have particular duration. Okay. So earlier we say. Then there is a difference between the two pulses here. So if supposed to be another, then we can say that Tk plus one. Okay. So this duration is about we supposed to consider that Tk here. Tk plus one is about your pulse duration. So now for a given particular signal received at a receiver, we supposed to find out that a false alarm probability PFA, and that false alarm probability can be expressed in terms of a what will be the time of the envelope here. Okay, that's about it. So that's why we can express that it false alarm time with respect to the what will be the average duration of a threshold crossing by the noise. Okay, so that is to be obtained here. So in that case, that average duration that is to be approximated with respect to the bandwidth of a IF. Okay, so that's why we can find out a false alarm time. Okay, that is about false alarm TFA with respect to the bandwidth of a your IF, and then this is about a VT square by twice. So VT is nothing but what? This is about a threshold voltage. Above this threshold voltage, whichever the signal is detected, that is to be find out here. And psi 0 is nothing but what? That is about the mean square value of a noise voltage. This is about a mean square value of a noise voltage. So generally we are getting the signal. Okay, so this one likewise we are getting the signal. Okay, so then in that case, what will be the mean square noise value of the voltage? That is nothing but a psi 0 here. That is to be obtained. So this is a T of a, that is about a probability of a false alarm detection, and this T of a is nothing but the a false alarm time here. Okay, and the false alarm time is nothing but the or it is depending upon the probability of a false alarm as well as the a bandwidth of the IF here. So again we can say that this bandwidth, okay, it is related to the bandwidth of a IF. Again it is related to the what will be the threshold voltage we have considered. Okay, so for the given particular signal. So we should know that what is the threshold. Okay, so that we are able to detect a signal within a particular frame of or within a particular period of a time there. Okay, that echo signal is to be detected. So now we talk about that what will be the probability of a detection of a signal here. So in that case, we supposed to know that what will be the highest value of a signal. Okay, that is about a amplitude we can say, and what will be the a noise voltage. So and then through that we can find out a probability of a detection of a signal. So here is a some particular level is to be identified initially, and from that we can find out the probability of a detection of a signal there. The next topic we should consider here, that is about the we need to modify the radar equation with respect to the minimum detectable signal, and then we need to consider the same radar equation or a modified radar equation with respect to that how many number of pulses we supposed to be find out here. Okay, again we modify the R max here. So in that case we supposed to know that how many number of pulses return from the target. So that's why we need to know about that integration of a radar pulses. And then from the integration of radar pulses, we supposed to describe the a radar equation again. So number of pulses return from a given particular object. So this one we consider that a radar here, and we have the object here. Okay, so we have the object here, and we say that number of pulses we are transmitting and we are getting the echo signal. Now, how many number of pulses sent by the radar? Okay, these are nothing but a rectangular pulses generally sent by the radar, and for each and every rectangular pulses, it has some particular duration, and then it has some particular repetition interval, pulse repetition interval. Okay, pulse repetition interval. Okay, this one in between the pulses there. Then we need to know about how many number of pulses transmitted from the radar to the object, and then how many pulses or echo signal received by this radar through the object. Okay, so it is depending upon that what type of a antenna we are using here. Means antenna is scanning. Okay, generally we say that we are using a parabolic antenna. So about we can say that parabolic antenna, and this parabolic antenna it has some particular a beam width. So generally we are expecting that a narrow beam. This is nothing but a we say that a beam width, and these are the half power point. So this is nothing but a beam. So within a particular beam width, how many pulses are received by the radar? Okay, how many pulses are received by the radar? Generally, what happens when we are sending a pulses to the object, then pulses, okay, the signal will be reflected in any other direction. Okay, so this is about a reflection of the signal. Okay, at any other direction. So in this particular case, so how many pulses scanned by the radar? Scanning is depending upon that what is the beam width of a radar and how many pulses transmitting from the radar. Suppose I am seeing 100 pulses are transmitting, and out of 100, suppose I am getting only a 10 pulses. Means 10 pulses received by the radar within a particular beam width. Okay, so we need to know about that for a given particular radar, what will be the antenna beam width and what will be the scan rate. Okay, scan rate means what? It is just like a rotating your antenna. Okay, rotating your antenna. So that's why we're supposed to find out what will be the scan rate of an antenna there. So generally, number of pulses we are sending, but we are receiving the less pulses at the receiver. So that's why we need to know about that how many pulses return from the given object that are depending upon that what will be the pulse repetition frequency, okay, as well as that a beam width, as well as that a scan rate, okay, of a antenna there. Now we can consider that here we have a theta b, that is nothing but a antenna beam width, and fp is nothing but a pulse repetition rate. Okay, fp is nothing but what? Pulse repetition rate. Okay, this is about fp is pulse repetition rate. Theta b is nothing but the beam width, and a theta s is nothing but a scan at a rate of a whatever the theta degree, because that antenna is scanning at a rate of what? A theta s. So that is about a scan rate. Okay. So now generally we consider that a antenna is rotating means what? A 360-degree rotation. Okay, so circular. Okay, so it is rotating always. So now what will be the and rotation? One rotation, or you can say that how many revolution per minute by the rotating antenna. If it is if it is rotating a 360-degree rotation. Then the number of pulses received, that is depending upon that how many pulses hit by the radar. It is rotating. So sometimes we say that it comes from the different, okay, it reflecting. So that's why it is goes in a different direction. Divert. Pulses are diverged here. So when we are receiving at this particular radar, but your antenna is rotating. So within a particular period of a time, it is to be hit to the object. Okay. So that's why the number of pulses received, that are depending upon that how many hits per scan or a pulses per scan. How many pulses received per scan by the antenna there. So I am supposed to consider that. Suppose I am sending 100 pulses, but we are receiving only a 10 pulses now. So that n 10 pulses n is nothing but a 10 here, and that are depending upon that what will be the pulse repetition rate, then what will be the theta s, and then what will be the a theta b. Okay, so this way we can find out. So then number of pulses received at the receiver. Okay, means number of echo signals we are getting. So that pulses or number of echo signal is to be summed at a receiver there. So summing of all the received pulses come from the target. That summation is called as the integration of the pulses at the receiver. Okay, so that integration is depending upon that what will be the signal to noise ratio at the receiver side. Okay, signal to noise ratio at the receiver side. Means we say that it's supposed to be a single pulse we are receiving. Then what will be the signal to noise ratio for the single pulse? A signal to noise ratio for the n number of pulses. So in that case, the integration efficiency is depend upon that how many number of pulses integrated with respect to the signal to noise ratio. So that we can write here the integration of pulses ei, okay, with respect to that a n pulses are integrated here with a integration factor. We supposed to consider that how many number of integration of pulses with respect to the a signal to noise, that is about s of n number of pulses s by n with respect to the n number of pulses we are receiving. This is a integration efficiency of a device, because we are getting a n number of pulses received, and we supposed to find out that what will be the signal to noise ratio for the pulse 1. If there are the n number of pulses, then what will be the signal to noise ratio for the n number of pulses? Means combining the all the pulses or adding all the pulses. Integration is nothing but the addition or a summation of all the a pulses there. Okay, so that's why we can use instead of a s by n1 here, so it is nothing but a s by n of n here. Okay, signal to noise. That is nothing but a integration. N number of pulses are integrated there. And that all the pulses generally we supposed to be received without noise. Okay, we supposed to consider that it is to be received without noise. So then in that case, we are expecting that pulse with integration factor with respect to the signal to noise ratio with a n number of pulses and a one pulse. Then we can modify a R max, modify the equation now. So earlier case we have written that the equation, that is a PT G AE sigma. I supposed to consider instead of 1 by 4, I will consider R raised to 4 here. We have a 4 pi square, then K T0 BF N, and earlier we say that S by N. That S by N, because we have considered that signal to noise ratio for the whole pulses. So that's why f by n with respect to n here. Then we can rewrite the equation s by n replaced with the s by n by n. So in that case, we replace the equation here. Okay. So I will rewrite the equation again here. So Pt G A E sigma. Okay. Sigma. Then we have the n E I. Okay. Here we can say that n E I of n here divided by same 4 pi square bracket square then k T0 B F n with respect to s by n by 1. Okay, now this one is about a modified equation of a radar here. Okay, so this one s by n we supposed to consider that for the n is equal to 1. Okay, so likewise we are modifying a radar equation here with respect to the what will be the integration of a pulse factor, and here we have expressed here the bandwidth and a noise figure here. Okay, so this way we have improved the radar equation. So we will talk about the a radar cross section of a target, then a transmitter pulse, how many transmitted power there, and everything in the next lecture. So with this, we stop here. Thank you all of you.